Hello folks, today we're talking about an introduction to determinants, material from 3.1. So let me recall what we know so far. So recall if A is a 2 by 2 matrix, so it looks like A, B, C, D is a 2 by 2 matrix. We have this thing called the determinant, then det A is this, right, this number I get by taking the product of the diagonals minus the product of the off diagonals. That's called the determinant. And what we know is that A is invertible if and only if det A is not equal to 0, right? And so the story that we want to, the question we want to ask and answer today is, is there something similar for arbitrary n by n? Okay, so the answer is yes, and we're going to give that answer today. Let me point out that remember that A being invertible is the same as saying that you have n pivots, right? That the matrix reduces to the identity matrix. So what we want here is a number associated to an n by n matrix A that detects basically if A has n pivots. And of course, that's the same as reduces to the identity matrix In. Because if you're n by n and you have n pivots, that's the same as saying that you reduce to the identity matrix. Okay, so that's the kind of thing we want, is this number. Now, let me maybe kind of motivate this with a 3 by 3 example. So let's take a 3 by 3 matrix. So let's see, if A is, what's a 3 by 3 look like? It has an entry in the first row, right? My convention is that A12 means the entry in the first row, second column. My second row stuff is this. My third row is this. So this is an arbitrary 3 by 3. And what I'm going to do now is row reduce, with these kind of funny looking entries. This is just a general, an arbitrary matrix. When I row reduce this thing, I get, it's going to be kind of a mess. But what I want to do is reduce to echelon, of course. When I do that, I get an A11. I'm not touching the first row. Of course, I have a 0 here in the second row. It turns out this entry is going to be A11, A22 minus A21, or A12, A21. This entry is going to be A11, A23 minus A13, A21. It's not so important what that is. And then, of course, I get a 0, 0 here. And then here I get a real mess, but I'm going to call it A11 times delta, okay? Where delta, okay, so delta is going to have a lot of symbols in it, but what is it? So delta is going to be A11 times A22, A33 minus A23, A32 minus A12 times A21, A33 minus A31, A23, and then one more term plus A13 times A21, A32 minus A31, A22. Okay, so like I said, it's a big mess, but let's see if we can find some patterns here. So the first thing I want to point out is that, remember, I want to know when does this thing have 3 pivots, and the fact is that A will have 3 pivots if and only if this number delta is non-zero. Okay, so of course if delta is 0, that's gonna mess up this column here, because if delta is 0, it's gonna make this a 0, which means I'll be missing a pivot in this column. But in fact, if delta is non-zero, we can assume that A11 was non-zero because we would have put it up into the upper left corner. So that'll be non-zero, and in fact, it also makes this non-zero. So if delta is non-zero, actually we get what we want, these 3 pivots. Okay, so delta is going to be the thing that we care about. But it looks like a mess, but let me, like I said, let's find some patterns here in delta. So for this, let me make a definition. So define what I'm going to call Aij to be well, in general, an n minus 1 by n minus 1 matrix obtained by deleting the ith row, jth column. So if you give me I should have said that A is going to be an n by n matrix. What I do is I can delete the ith row and the jth column, and I get a smaller matrix, right? So for instance, if I had that A as A11, A12, A13, A21, A22, A23. Okay, so if this is A, then what do I get, say, for A, I don't know, let's do 2, 3. So what I'm going to do is I'm going to delete, well, let me do 1, 3, actually. So I'm going to delete the first row, third column, and what I'm left with is just, well, what you see. So A21, A22, A31, A32. Okay, so that's what I mean by Aij. Now notice, when we go back to this expression up here, these things in the parentheses look like little determinants of 2 by 2s, right? So look at this. So for instance, this A13 looks like, you know, if I take the determinant of this, it's actually this thing here. So this thing here is actually the determinant of what we had here. It's det A13, right? Because I took the product of the diagonals minus the product of the off diagonals, and I get that number. Okay? And look at this. This is actually the determinant of what I get when I remove row 1, column 1. Okay? So if you go down here, remove row 1, column 1, take the determinant, you get this. So what I'm seeing here is every term I'm seeing something, an entry times the determinant of a smaller matrix. Right? And what did I do here is I started A11, A12, A13. So I went along that first row, and then I took the determinant of the corresponding Aij. Okay, so to summarize, what do we see here? So this is going to be our definition. Suppose A is an n by n matrix, and I suppose I should say n is bigger than or equal to 2 here. Then the determinant is given by, the determinant of A is given by, so what do I do here is I say, well, det A is going to be, okay, so what do we just say here? What I'm doing is, you can't quite see it here, but if you go back to what I have here, right, I'm going along the first row of that matrix and doing that thing, right? Take an entry times the corresponding Aij. So what that looks like is going to be, well, A11 times det of A11 minus A12 times det of A12 plus, and then you go, you know, plus minus, the last thing will be, well, I can say that this is actually plus minus 1 to the n plus 1 of A1n times the det of A1n. Okay? So that's the, that's the mathematical way to do this. But again, it's a sum of a bunch of terms. I should say that there's n terms here. So if you're an n by n matrix, you have n terms. And each one corresponds to an entry in that first row. Okay, that's the idea. Let's do this with an example. I think that's how you make sense of this. So let me try to put that here, and we'll do an example. So let's take A to be, I don't know, 1, 5, 0, 2, 4, minus 1, and 0, minus 2, 0. Okay? And let's find, the determinant. Some people write absolute value of A as the determinant, so just to keep that in mind. Okay, so what do I do is I go along that first row. So here's the first row that I'm kind of expanding upon. And what I do is I say, well, det A is going to be, so first I say it's 1, right? And then times the determinant of, I'll write A11. I'll figure that out later. Then I'd take minus the next term, which is minus 5, times the determinant of A12. Plus, keep going, 0 times, well, it's 0, but it's times the determinant of A13 if we cared about that. Now, what are these determinants? Well, this is 1 times the determinant of A11, remember, is remove row 1, column 1, and what you get is determinant of 4 minus 1 minus 2, 0. Minus 5 times the determinant of A12 means I cross out the first row, second column. You get 2 minus 1, 0, 0. Okay? And then the idea is, well, these are just 2 by 2s. We know what to do. Okay, so this is going to be 1 times, what's the determinant here? That's 0 minus 2. So minus 5 times, well, that's 0. So you're actually minus 2. Okay, that's your determinant. Okay, so that's the idea. I should say that when, this formula works for any matrix of any size. So when your matrix is bigger, you actually will have, another recursive step. So this definition that I'm giving always says that the determinant of an n by n is determined by the determinant of n minus 1 by n minus 1. So this is, what you call a iterative or recursive definition that I then, run. I might have to run it again when I'm determining the determinant of this guy. But then eventually when I run this algorithm, I have all 2 by 2s to look at, and I'm good to go. Okay, so the next thing I want to mention is that, in fact, I don't have to take that first row as a, kind of the thing that I expand upon. So in fact, I can use any row or column in my calculation. Okay, so again, if I have the matrix A, I chose that first row, but in fact you could do the second column or whatever you want. And for that, let me define something. So definition, what's called the ij cofactor of the matrix A is given by the following. So it's a number Cij, and all it is minus 1 to the I plus j times the determinant of that Aij thing. So again, I know a lot of symbols here, but I'll show you what this means in an example. And the fact is, the theorem or the fact is that, like I said, to calculate det A, we can use any row or column. And what I mean by that is, well, if I use the ith row, what I'm going to look at is det A. What it's going to say here is that I can now take these, right, instead of taking the first row, which would be A11, A12, A13, I can take AI1, the ith row, times that cofactor CI1 plus AI2 times the cofactor CI2 plus ... plus up through AIN, cofactor IN. If you use the jth row, then the determinant would be, well, what I'm going to do now is expand along the jth row. So that means that I'm looking at A1j times C1j plus C2j, the cofactor C2j, plus ... ANJ, CNJ, okay? Now notice that there's a plus minus kind of factor involved in there, and I'll show you a way to think about that right now in an example. So let me do that. Let me actually show you an example of this where I look at the matrix we did up here. So for example, let's use let's use the well, I should say that, when I'm picking which row or column to use, I want to pick one where I have the most zeros, right? So we already saw that having lots of zeros is useful. So let's use the third column of A to calculate det A. Okay, so now I'm going to use this column here. And what I know is that, well, in terms of that plus minus pattern, what I'm using is there's a kind of hidden checkerboard of pluses and minuses here. So what I'm going to do is I'm going to use that first column with the plus minus pattern that I see here. So det A is going to be, so going along this first column, well, it's just 0. Now it would be times det of, right, the thing that I see by removing the first row, third column. So this would be 2, 4, 0, minus 2. Of course, I don't care. And then I'm going down. I see a minus sign here. So that'll be minus times minus 1 times the det of what happens when I remove the second row, third column. So 1, 5, 0, minus 2. And then this would be plus 0 times, well, I don't care, but it would be det of 1524. Okay, so the point here is that these go away. My life is pretty easy. So this will just be 1 times the determinant of this, which was 1 times minus 2 minus 0, which is minus 2. And so, you know, pretty cool. We get the same answer that we just had up here by using the first row. Minus 2 is what we had, and we still have minus 2. Okay, so next time I'll talk a bit about the properties of determinants, do some more examples. We'll see you then.